Hello, so today we're gonna be solving an integral from the MIT Integration Bee, and this integral contains a nasty product, which is the product from k equals 1 to infinity of cosine x over 2 raised to k. So this integral is an unusual integral, but there are numerous approaches in the internet that exists for these kinds of integral. And although I'm gonna be using a log differentiation technique. Okay, so how this works? How this works by um well, let me just write the integral. So integral from 0 to pi over 4 of x times this product, and next we will just let u equals this product. Since I mentioned we will be using log differentiation, we will take the natural logarithm on both sides. It's ln u. It's gonna be ln of the product k equals 1 to infinity cosine x over 2 raised to k. Okay, so what does this do to our product? Notice that we are taking the log of a product here. So if you remember with our log properties, log AB is equal to log ln A plus ln B. So this means that the natural logarithm of a product is the summation of its ln's. This is a bit of a notation abuse, but yeah, you get the idea. Alright, so we now have summation from k equals 1 to infinity of the ln of cosine of x over 2 raised to k, and then that's it, ln u. But now, since I mentioned that we will be using log differentiation, we will differentiate this. Okay, so on the left hand side, we will have u prime over u, and on the right hand side, since k is independent of x, we will just keep it. So k equals 1 to infinity. The derivative with respect to x, ln cosine x over 2 raised to k. Alright, so we have u prime over u, and this. Okay, so since k is a constant, and we will be using chain rule here, so first I'm gonna have 1 over cosine of x over 2 raised to k. Let me just rewrite it properly. Times the derivative of cosine x over 2 raised to k, which is negative sine of x over 2 raised to k, times the derivative of x over 2 raised to k with respect to x, which is 1 over 2 raised to k. Alright, so now we have u prime over u. That will be the summation from k equals 1 to infinity of negative, well, since sine over cosine here and the same arguments will have tangent, but I'll just write 1 over 2 raised to k here first, and then tangent x over 2 raised to k. Alright, so that's now the 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 expression we have. Okay, so what do we do from here? We utilize this identity that cotangent theta minus tangent theta equals 2 cotangent 2 theta. Okay, so this gives us a shot at having a closed form for our summation. Okay, so tangent theta here is cotangent theta minus 2 cotangent 2 theta. And if we let uh, theta equals x over 2 raised to k and match our form here, you should have negative 1 over 2 raised to k tangent x over 2 raised to k equals negative 1 over 2 raised to k times this one with theta equals x over 2 raised to k. So cotangent x over 2 raised to k minus 2 cotangent 2 times x over 2 raised to k. Alright, so simplifying this one, we should get negative 1 over 2 raised to k cotangent x over 2 raised to 2k minus 2 cotangent that's times 2 raised to 1 minus k, but if we rewrite it in the denominator, we should get x over 2 raised to k minus 1. Alright, and if uh, we simplify it more, we should get positive 1 over 2 raised to k minus 1 cotangent x over 2 raised to k minus 1 minus 1 over 2 raised to k cotangent x over 2 raised to 2k. Okay, so this is now the equivalent of our function in the summation symbol. So our new equation now should be u prime over u is the summation from k equals 1 to infinity. Since these two are equal, we will just replace it with 1 over 2 raised to 2k minus 1 cotangent x over 2 raised to k minus 1 minus 1 over 2 raised to k cotangent x over 2 raised to k. And then we notice that this is a telescoping sum. Okay, so let us list a few terms, the first few terms, so that we can see that happening. Okay, so when k equals 1, we should get cotangent x minus 1 half cotangent x over 2. So that's when k equals 1, and when k equals 2, we should get 1 half cotangent x over 2 minus 1/4 cotangent x over 4, and then when that's plus right there, and then when we get x equals 3, we should get 1 over 4 cotangent x over 4 minus 1 over 8 cotangent x over 8, and so on. So you can clearly see that this cancels out, this cancels, and as we reach infinity, uh, our product, we just write the equation u prime over u. Uh, we have the first term, cotangent x minus, well, this will keep increasing, and also this. But if, well, there is a limit, k to infinity of 1 over 2 raised to k cotangent x over 2 raised to k. Okay, so yeah, that's that now. But what is that limit? Okay, uh, you could use L'Hopital's, I think, but um, we will use this fact that as uh, theta approach, I don't know, let's use cotangent theta uh, is approximately 1 over theta as theta approaches 0. Okay, okay, so our argument, which is x over 2 raised to k, when k approaches infinity, this theta approaches 0. So, so now this means that cotangent x over 2 raised to k is approximately 1 over x over 2 raised to k as k approaches infinity. Alright, so our equation now should be u prime over u equals cotangent x minus this limit k approaches infinity 1 over 2 raised to k times 1 over x over 2 raised to k, and then this should cancel out. So u prime over u should be cotangent x minus, well, since k is independent of x, even if it approaches infinity, it should still be 1 over x. Alright, so now we have that u prime over u equals cotangent x minus 1 over x. To get u, we should integrate back. So integrate cotangent x minus 1 over x dx. So integral u prime over u, that's ln u, and cotangent x, that's ln sine x minus ln x plus c. And now uh, ln u equals ln sine x over x plus c. But then we can just exponentiate it to get e is ln u, e raised to this, and this is a constant, so yeah, can this cancels, so we get u. This also cancels. Then uh, technically we should have here e raised to c times sine x over x, since this is property of exponents. Alright, So now our problem is this constant. What is that constant? E raised to c. Well, we should we should know that we, as as x approaches 0, u approaches the infinite products of cosine of zeros. So an infinite cosine of zeros multiplied to each other, just one. 1 times 1 times 1 times 1. So that's 1. So, and also, and sine x over x approaches 1 as x approaches 0. Okay, so now we will have the equation 1 equals e raised to c times 1, which then implies that e raised to c should just be 1. Okay, so that was a save. So now we have u equals sine x over x. So now our integral, we can just replace u by that. So the integral is from 0 to pi over 4 x times the product k equals 1 to infinity of cosine x over 2 raised to k dx should just be the integral from 0 to pi over 4 x times sine x over x dx. And whoa, look at that. So x and x cancel. So we get 0 to pi over 4 of sine x dx. And that is negative cosine x evaluated from 0 to pi over 4. And that should be negative cosine of pi over 4 is root 2 over 2. And cosine of 0 is 1. So our integral is just 1 minus root 2 over 2. Yeah, it's beautiful. So yeah, that's it for now. See you again. This has been Euler Phil.